Hey, so before we jump into today's video, I just want to remind you that there are timestamps. I'm going to separate the video into different sections, so you can use the timestamps below to navigate to different topics or to save your place because it's a pretty long interview. So if you decide you want to stop somewhere and come back to it another time, yeah, timestamps are below, and there's also a couple things that we talk about, certain books or authors, websites, etc., and those are going to be linked in the description down below as well. All right, welcome everyone to the newest episode of Math Talk. I'm here today with Jack Pope, who recently got his PhD in physics, but is also one of the creators of CryptoHack, which is a really cool little website all about learning cryptography. So yeah. Welcome. And I guess maybe just to start off briefly, if you want to just in a few words explain your current say research in PhD and just a couple words on CryptoHack.
Yeah, sure. So I spent my time during my PhD studying black hole solutions to supergravity. Very, very roughly, what this looks like day to day is making an ansatz for a metric. So deciding a set of symmetries for a differential manifold, and then taking a set of differential equations, which for physicists we call Einstein's equations, but mathematicians, these are just second order nonlinear differential equations. And the balance in research is giving the manifold enough symmetries that we can solve the differential equations, but leaving enough freedom in our parameter space that we don't make something completely trivial.
Right.
A nice way to think about this is if you impose that your manifold has maximal symmetry, then the resulting space-time is almost completely determined by Einstein's equations. You have three options. Either constant curvature, which is positive, negative, or zero. So basically spheres, hyperbola, or just flat space. And if you have space-time, then these things are like pseudospheres. And you have the Minkowski space-time rather than the Riemannian flat space. But yeah, you get what I mean. Maximal symmetry, not very interesting solutions, but obviously a key component to studying stuff. And on the flip side, if we don't impose any symmetries at all, we have these completely gnarly differential equations that we don't know how to solve. We can start trying to plug them into computers, but my work was really looking at these analytic pen and paper solutions. And in particular, when I was looking at finding solutions, I was kind of geared towards thinking about a particular property of these solutions, which is nice way to contextualize it. So very, very flatly, we can think about black hole solutions as thermodynamic systems. And in a certain sense, someone might think, well, yeah, of course, because they're kind of related to stars and stars are hot. So I'm happy with it. But when you actually start unpicking it, the statement that black holes are thermodynamic is really strange, because the kind of my first black hole definition is that they're these objects from which nothing can escape. It's a region of the space, and it doesn't. I mean, maybe I should dial it back. If there are people listening who aren't exactly sure what a black hole is, the way that I try and explain it to people is, imagine you're stood on the surface of the Earth and you've got a bag of baseballs and you're throwing them into the sky. Most of the time when you throw your baseball, it will eventually hit the ground again. But if you throw the ball hard enough, and what I mean by this is if you make the ball move fast enough, so we need to give it a certain velocity, we say that the object has a velocity greater than the escape velocity, and it escapes the gravitational field of the Earth. We can essentially send the baseball into orbit by throwing it hard enough. A black hole is simply a object which has got such a huge amount of mass in such a concentrated amount of space that the gravitational field is so strong that even if you threw the baseball at the speed of light, the baseball would never reach orbit. It would always come crashing back down to the surface. So when we mix this with the kind of special relativistic notion that nothing goes faster than the speed of light, you then realize nothing can leave the surface of a black hole. There's all sorts of other slightly more delicious mathematical definitions of a black hole, but this is really, if you want to be thinking about what these things are, they're just things that are too heavy to escape from. Yeah, so when we're thinking about it like this, suddenly the idea of saying that they're thermodynamic, that there's this kind of radiation coming from them, then feels really uncomfortable. We define it as something that nothing can leave, and then I come into the podcast and say that we're interested in looking at the kind of thermodynamic properties of these things, and this is the core of the revolution that Hawking brought about in the 70s when he started studying Hawking radiation. It's one of these things that only really appears when we consider semi-classical physics. No, semi-quantum, we call it semi-classical. But when we start bringing in quantum-like effects into our descriptions, we start seeing these things. But from a much more philosophical background, the interest in the thermodynamics of black holes is that the thermodynamic laws of a black hole manifest as geometric statements. They are absolute statements about the geometry of our solutions. So going back to the fact that we have this manifold and we define the metric from a solution of Einstein's equations, we can derive a set of properties of the geometry of the solution, and we can build a set of laws about the solution. Thermodynamics in a kind of standard context, which you maybe cover when you're at college or even at school, depending on how your school is a statistical thing. It's a kind of rough approximation. We don't say something has heat in any kind of concrete way, but if you take enough atoms and pack them into a space, we can say that something kind of has temperature in a kind of average-like way. So the appearance of this statistical-like behavior as a concrete law of geometry is incredibly interesting. And fully understanding this is, I mean, from my point of view, really comes from kind of like trying to stretch this analogy. So if we're saying black holes are thermodynamic and that there are geometric properties of a black hole that look like thermodynamic laws, how far can we stretch this? Are there exotic black hole solutions that don't do this? Are there specific parts of thermodynamics that we haven't seen yet? Why haven't we seen those things? To focus in on this, my research was looking at, or continuing, my supervisor's previous student had been looking at these things, these black hole solutions, which had a relationship where the entropy of the black hole was zero when the temperature was zero. This is to do with the third law of thermodynamics. And basically, it comes in two versions. The weak third law says that we should minimize the entropy in the zero temperature limit. So when we cool down our system to be zero temperature, the entropy should be at a minimum. The strict third law says that when the temperature is zero, there is a unique ground state and that the entropy of the system is zero. So a quick recap on entropy is the entropy basically counts the disorder of the system, and zero entropy means a completely ordered system.
But now, so how is it that a black hole can have zero temperature if it has mass? Question one. And question two, I thought that also that the entropy of a black hole was proportional to the surface area. And so it sounds strange to me that either of those things could be zero if there's a black hole there.
Sure. So the zero temperature thing is actually less weird than it sounds. So you've already identified one of these equivalences, this notion of the black hole's area being related to its entropy. There's a slightly more obscure parameter called the surface gravity. The kind of physical motivation for this quantity is I'm hesitating because it brings in some relativity stuff. If I imagine I drop an astronaut into my space time, and I hold on to the astronaut with a rigid rod, so I can kind of like I can move him through space by moving where the rod is, and and he's being pulled towards the black hole from its gravitational force. The surface gravity is how much force I would have to exert on this rod to hold the astronaut exactly on the surface of the black hole. Now it gets a bit iffy because technically the force diverges for the astronaut, but if I imagine myself as an observer at an infinite distance, so now my rod is an infinite length, then the force is finite, and this is represented by the surface gravity. If this feels a bit weird, another way to think about this is the surface of a black hole mathematically is well, not always. Let's just say it is true, and if someone wants to correct me, then we can deal with it. Is always a Killing horizon, and a Killing horizon is a null hypersurface in a manifold whose normal vector is a Killing vector, and a Killing vector is a vector field which has a certain set of properties. It doesn't really matter. I mean, it's interesting for proving stuff, but in particular, there's just a normal vector, and the normal vector has some certain properties. And if we look at the derivative of the Killing vector, we see that it's proportional to the Killing vector itself, and this constant of proportionality is the surface gravity. So the surface gravity has a very concrete geometric notion. The surface of the black hole has a geometric structure, and we can look at a special vector field which is normal to the horizon, and looking at the derivative or the derivative of the vector field, we get some function, and evaluating this function on the horizon gives us the surface gravity. So it kind of this is a very geometric thing that kind of manifests in a physical interpretation of this kind of force to hold you in place. But what Hawking showed was that the black body radiation, the temperature of the black hole, was proportional to this surface gravity.
Okay.
So that was very roundabout, but there's this extra parameter, and when we look at the radiation, it's proportional to this. And when a black hole has zero surface gravity, we say that the black hole is extremal. There are a particular class of black hole solutions, and in fact, supersymmetric black holes always have zero surface gravity. And to answer your second question, yes, it's very weird that the entropy disappears. Almost every black hole solution we've ever found doesn't have vanishing entropy. They all have extremal black holes which have finite area density, and so satisfy the weak Nernst law. But I came to Liverpool, and I started doing this research, and Thomas, my supervisor, and his student Dave had been looking at these special solutions which, I wasn't going to go into the details, but I'm here now. So one of the ansats they had made for the manifold was that the horizon had planar symmetry. So rather than the black hole being kind of visualized as a ball located somewhere in space, it was a plane. So some Euclidean plane extending in 2 dimensions. Instantly, you're moving away from kind of physical black hole solutions. This is obviously, I mean, this is cutting all the way through space-time in 2 dimensions, right? Academically, it's interesting. And what they were able to show is, with a very specific physical setup denoted by the Lagrangian, and setting a bunch of properties in the ansatz they made for the manifold, they obtained a black hole solution, or a black brane solution, if we want to kind of talk about its symmetries, that had this surface gravity that could be taken to 0, and the area density of this planar solution vanished identically. So it's a particularly weird solution, and in a sense, there's singular properties associated with this. But the reality is rather than maybe worrying about the causal structure of the solution in this limit, it was the thermodynamics of the solution which were interesting. So I guess if you really wanted to hold on to the physics, another interpretation might be the black hole vanishes in the extremal limit. Like, there is no black hole, there is no entropy. But that in itself is interesting. If we look at the kind of general class of these extremal solutions, they don't vanish. So so this is where I was, and I started kind of generalizing the Lagrangian, which is this kind of, if you don't do much classical mechanics, it's basically a kind of description of the system with the matter fields and stuff in it, and tweaking what I was pumping into the solution and then looking at how I could solve the equations of motion and see what happened. And my research very naively was, well, here was one interesting solution. How can I kind of stay locally in this area, changing a few little things and seeing, do I get anything non-trivial as a result of this? And for 4 years, I basically just followed my nose. This is really, really a kind of like, try changing something, see what happens. Is it interesting? Is it not interesting? And in particular, what I found was a kind of non-trivial change I could make was how many charged vector fields my solution was supported under. So what I'm really saying physically is, if I have a black hole, the kind of next step on, if you do relativity, is you first study the Schwarzschild solution, which has no charges. And if I couple my solution to an abelian vector field, what I'm actually doing is I'm putting in some electromagnetic charges onto my black hole solution. And so I can go from having a black hole which has a mass parameter to a black hole which has a mass and an electric/magnetic charge. Standardly, you just stick one on, and this abelian vector field represents that. But within supergravity, you have additional matter multiplets you can put in, and kind of purposely being hazy here because it's not that important for the research or for the listener. All you need to know is I can put as many matter fields on as I want, and I chose to put kind of NV of them, NV vector multiplets, and I could choose how many of them had charges. So the original solution had one charge, and then I found that if I didn't want to stray too far from the solution generating technique, I could have 2, 3, or 4 charges that all had a slightly different structure. And then the question was, if I change how many charges are present, how much of the solution changes? Is it an identical solution and I don't really learn anything new, or does it completely break? And the 2-charge solution broke this special behavior of the zero entropy limit. So by adding the additional charge, the solutions changed. The geometry of the black hole was different. It was still planar, but the functions appearing within the metric had a different form. And when you compute the surface gravity and then take that to be 0, you find that the entropy doesn't vanish, but it's instead finite. So it was interesting because I had made a kind of fairly small change, but I drastically changed the thermodynamic properties of the solution. And then I looked at the 3 and 4 charge solutions, and things changed even more. And in fact, it very, very loosely, it seemed to kind of turn the geometry inside out. And I'll qualify this with a simpler discussion. So to go all the way back, the most simple black hole we can describe as the Schwarzschild solution, and it's a spherically symmetric distribution of matter with an event horizon located at a finite point in space. So what this means is we leave the surface of the Earth in our rocket ship and we fly towards the nearest black hole, and the edge of the black hole, the boundary, is we call the event horizon, and we can think about this as just being a place in space. Doesn't really matter. We can go there or we don't have to go there. If we choose to go there, we can get infinitesimally close to the surface of the black hole and then change our mind and leave. But as soon as we make contact with the edge, we are unable to leave this region anymore. We're stuck, basically. We can think the point of no return. Now, the thing which maybe gets talked about less is, so the center of the black hole has this divergence in my scalar fields of my solution. Basically, I get something that blows up. I can define a curvature scalar, which is well defined everywhere except a single point in my manifold. And this is the center of the black hole, and we totally don't understand it as physicists. And this comes up all the time. And if I think about a black hole in isolation, this singularity could be the point r equals 0. So I'm using spherically symmetric coordinates. The center of the black hole is r equals 0, and then the horizon is at some r equals, I mean, for the short solution, it's 2m, but some horizon radius rh, let's say. So outside of rh, I have the usual spacetime, and from an infinite distance, the black hole disappears. I can't really see it. We call this asymptotically flat. Then I get to the surface of the black hole, and I can understand the singularity at being at r equals 0. But the key thing which happens is outside of the black hole, the point r equals 0 is a point in space. Like the horizon, it's a point that I can ignore. I can move away from it, just like I can move to my door, or I can choose not to move through my door.
Right.
But as you know, regardless of where we choose to move, whether I go through the door or I sit here on Zoom with you, we're always moving through time. We don't really have a choice. It's just happening. There is no movement through time that we have any control over. It's just this kind of ticking clock. When you cross the killing horizon, when you go through the event horizon, what we find is that the coordinate r is no longer considered space-like, but in fact becomes time-like. And what this means is that this singularity in the center, although we think about it as a point in space, we think about it as the center of the black hole. Physically, what happens when we cross the event horizon is the singularity becomes a point in time. And so one way to think about this is suddenly you're inside the center of the black hole, and you can do what you like moving through it. But whatever happens, you're eventually going to reach the center of this black hole. In the same way that we can't stop the hours from progressing, when you cross the event horizon, you can't stop reaching this center point. It's not a place that you can visit. It's a place that you're heading towards inevitably, just like the end of the day. And this isn't talked about, and it's actually pretty weird. Like the idea that we can kind of try and describe the center of something as a place, but actually once you go inside, things seem to go topsy-turvy, and the thing that you thought was a place is actually time, and thing that you thought was time you can then move through, but obviously you can't leave that region, so it's not like you can travel through time and then pop back out. Right. I'm not talking about time travel here. I'm just saying that your orientation changes.
Right. So what your choice then is basically in how long it takes to hit the center.
Yeah, you can
and
kind
that
of
would be, and so I guess the upper bound would be given by like a photon that's crossed the horizon. It's, if it were to try and attempt an escape, that would sort of give the maximal amount of time that any particle or observer could experience before colliding with the singularity, right?
Yeah, I feel so definitely one way to help yourself is to give yourself some angular momentum. Then you can think about it as like spiraling around the center rather than going straight in. I feel like there might be some kind of paradoxical thing where if you point your motion directly away from the black hole, that's the shortest path, but I actually can't remember. I'd have to do the calculation, but things get pretty weird. Yeah, so I don't want to go on record and say because I can't remember. It's kind of like master's level homework problem. Look at the longest geodesic within the black hole, and I think you get something which feels counterintuitive, but maybe it's something else that I'm forgetting. Right,
but I guess the point is there is some finite upper bounds, right? No matter what, after some finite extent of time.
Yeah. With the caveat that we really don't understand what happens when you get to the center.
Right.
You might get to the center and bounce around and be able to stand there for an infinite amount of time. So our classical description of the solution breaks when you get to the center, but potentially if you were an invincible photon and you get sent into the black hole, you could just loop around in the black hole for an infinite amount of time. You just can't leave the horizon.
Right.
So that's the kind of singularity that we know and love from sci-fi and pictures, and recently there was the new telescopic picture of a black hole, and in the center of that is one of these singularities if our current description is good. And then when you look at the solutions which I was continuing, this was the same singularity we were finding. Okay, there's a bunch of other kind of slightly less physical stuff going on, the planar symmetric horizon and the extra gauge fields which are coming from the supergravity theory. But the kind of super overview is there was still an event horizon at a finite point in time, and there was a singularity that was this space-like singularity. When you increase the number of charges, and this is when I was looking at the 3 and 4 charge solutions, and I'm talking about it now like it was natural to see, but it took a long time for me and my supervisor to unpick this all. But what you find is the singularity is still there, but the singularity becomes time-like. And to put this in context, the story is now you begin asymptotically far away from your black hole solution. But the horizon is now no longer a point in space, but it's rather a point in time. We talk about these horizons as cosmological horizons. And so unlike before, where our space person had the ability to go to the black hole or to go back home, this space-time solution is better thought of as something which is contracting and expanding. And the observer inevitably crosses the horizon at some point in time. Again, not all paths are created equal, but if you follow a geodesic, you will eventually, I mean, every time-like curve will eventually cross the horizon. How long it takes is up to you, but you will cross it. But now the interesting thing is when you cross the horizon, this same thing happens. The time-like and space-like behaviors of these coordinates switch, and you end up in a new space-time which is static. Time doesn't change the manifold anymore, and there's a singularity, but this singularity is located at a point in space. And so what this means is you can now go up to the singularity. You can wave at it, you can throw your lunch into it, but you can just turn around and then walk away. And actually more than this, if you study the causal structure carefully, what you find is the singularity is effectively repulsive. So what you do is you fall through the horizon, you end up at some minimum distance, and then at this point you find that naturally you're then pushed away from the singularity and out of the horizon into a new region of space-time. And then someone's going to go, I thought you couldn't leave black holes, and this is slightly different, and the two regions are causally distinct, so you still can't go back to where you were, you just end up being in a new universe. Maybe I can talk about that more if you find it interesting. But the takeaway is, rather than this conventional black hole, which you can choose to visit, fall through the horizon and then never be able to leave, there's now this black hole that you have no choice but to visit. You have to go through the horizon, but then you have this singularity you can kind of like wave to and disappear off. And this was super weird, because when we had solved the equations of motion, we had explicitly demanded that our solution was static. We didn't want anything to be time dependent, because it's usually simpler to study these static solutions. And what you find is when you solve the equations of motion, you end up in this very restricted patch of your manifold that is indeed static. And so we have this manifold, none of the metric components depend on the time-like coordinate, everything feels good. But when we start really studying this manifold, we notice that with some changes of coordinates, you can actually extend how much of the space-time that you're considering. You have this kind of very, very well-behaved local patch without any singularities or anything. And the more you probe it, the more you realize you can kind of extend beyond this. And when you start extending within this static patch, you actually find the singularity, which is very strange, because usually your singularity is behind a horizon. And then you go the other way and you find a horizon. So you're like, oh, I still have a horizon. I'm just on the wrong side of it. And this is what I mean by saying that it's inside out. We've solved the equations of motion for something which feels good, but actually we're in the bad bit, the space-time with the singularity. And we can analytically continue the geometry and leave in our description, our bird's eye appreciation of the space-time. And we end up in this dynamic patch of space-time. And we go, okay, well, this doesn't have the singularity. So this physically feels like how we should classify this. so to speak. Like, you wouldn't solve the Schwarzschild solution and say that the solution should be defined inside the black hole. You're outside the black hole and you're looking at it, and the same is true here. Okay, the way I solved a differential equation put me in a strange spot, but after moving out of it, you're in this new solution. And so the appearance of a cosmological solution after trying to ask for a static solution was very strange. And because it was unexpected, it took a lot of time to untangle, but it led to some really interesting questions, because cosmological solutions haven't been studied as thermodynamic systems in nearly the same way. Firstly, because we generally assume things are static or stationary, so cosmological stuff just doesn't come up that often. And secondly, even saying what's the thermodynamics of a cosmological solution feels really uncomfortable, because we think about thermodynamics as being done in a closed system. So then suddenly having everything depend on time feels like a horrible thing to do to yourself. but yeah, so that was kind of, I might take a break from talking about it now so that we can have more backwards and forwards. But my research kind of led here, and everything after that was then a bunch of kind of technical work on how far can we push this thermodynamic analogy, and I ended up developing a new formalism for the Euclidean action that allowed me to study real slices of a complexified space-time to study certain thermodynamic properties. And the upshot is the whole thing behaved exactly as we thought it would, despite the fact that maybe we would have said that it shouldn't have. So from the physicist perspective, I'm like, it still has a killing horizon. The geometry still satisfies these laws. Therefore, there should still be a thermodynamic interpretation. And then the other physicist goes, yeah, but you're not really doing thermodynamics anymore, and everything depends on time, and you probably shouldn't be doing that. So why should I have a thermodynamic interpretation? And this is really, I think, the beauty of this tension between the geometry of the black hole and this interpretation of a set of laws, and then the much older physical interpretation of thermodynamics as a thing in itself. And the question as a researcher is then, which one am I actually holding on to? And for me, the beauty of geometry is something which I'm much more inclined to hold on to than this kind of fairly loose statistical picture. And okay, the geometry is now saying something different. Maybe this isn't thermodynamics as we're used to seeing it, but it still seems to be doing everything that's there. And that was the kind of where my thesis ended up, developing these new tools to deal with slight differences in the causal structure of a solution, and how we can still think of these as valid thermodynamic objects. Yeah, so that was, I said I was chatty. So, yeah.
So I'm just wondering, so these black holes, I mean, they're non-physical, right? They're like planar black holes, but is there any way that this can inform us about black holes in our universe? You know, if we were to view these as some sort of limiting, like, is there any way to lift some insights from these, or is it just for the fun of the exercise?
So the solutions themselves will not appear. And even in formal analogy, the cosmological behavior of these solutions doesn't match how we want to try and describe the cosmology of our universe, for example. These really aren't appearing in the sky. That's probably the best way to talk about this. But the black holes that appear in the sky do behave like thermodynamic objects. And we can't go and hold a thermometer up to them. We can't, you know, there's a lot of there's a gulf in distance between where we are with our theory and where we are with what we can do experimentally with these objects. I mean, I spent 4 years studying a small part of these things, and then everyone celebrates that we have a picture of one of these things. So, like, I mean, don't get me wrong, it's an amazing image, but that's a huge difference, right? We sit and write pages and pages on advanced properties of special types of these solutions, and then we're still trying to get to grips with, can we even see these things in the sky? But there are some there are some kind of real world benefits to this research, which come much closer to the question of a quantum description of gravity.
Mm.
And not that I managed to prove that, I'd still be an academic if I did. but the question is really, so I mentioned earlier, we don't have this good idea of a singularity. The center it's too small, and by that point classical descriptions break down and we don't have a quantum description of gravity. We have some things with partial success. String theory is the one that gets quoted the most. There's also loop quantum gravity, which has a kind of alternative way of trying to solve the same problem. One says that matter is quantized and the other says that space-time itself is quantized. They both have benefits. I haven't studied loop quantum gravity in nearly as much detail, but some great people have. And when you're trying to develop a good theory, you need to have predictions. And the issue we have is that the energy levels that we're working with aren't particularly easy to come and find. Like we can't have a black hole sat in some laboratory and prod it. So what we want to try and do is we want to start getting cables connected between different areas to really start seeing whether these theories start to make sense. And this manifests itself beautifully in black hole thermodynamics because we have a quantum description of thermodynamics, which is called statistical mechanics. So we can describe stuff with classical thermodynamics very well, like engineers do it all the time. And it works most of the time for almost every scenario. You really don't need to go quantum for these things to work. But every now and again, when you need the accuracy to be high enough, statistical mechanics pops in and we can describe these solutions as collections of atoms, and their quantum behavior explains things that the classical description can't. And then the question is if a classical system seems to be doing thermodynamics, then a quantum description of gravity should be doing statistical mechanics. These theories should hold hands. There's no reason why they shouldn't. So Einstein's theory of relativity is classical. Everything is at a low energy limit. And when we study black holes, we start to see thermodynamics. So then the question is okay, if I have a quantum description of a black hole, I should then have a statistical mechanical interpretation for these things. I should be able to talk about, so entropy on a classical level is quite a fuzzy thing, but on a statistical mechanics level, it counts the microstates of the system. We can think about the quantum mechanical energy levels, and we can quantify this, and this relates to the entropy. If everything is in the ground state and stays there, then the entropy is 0, and everything is highly disordered and moves through the system, then we say that the entropy is high. And then the question is, okay, I'm developing a theory of quantum gravity. How do I explain black hole microstates? That's a good and solid question. And then string theory has some partial answers for this. There are some really beautiful calculations for specific black hole configurations which have a microstate description. And when you sum up the microstates, you get the entropy that we find in the classical limit. It's an incredible result. And this is where the theory really starts to try and, I guess what you can talk about is this kind of self-consistent description. We found some theory that seems to make sense in one description, and then we have this relationship to a whole different area of physics, which has a quantum description. So a quantum description of gravity should also start doing these things as well. And then this is really, I mean, I guess as you'll find out in your own research, when you start to try and solve the big problems, you have to do the little ones. And the little problem I tried to solve was exactly what is going on with black hole thermodynamics. Okay, I can take a very specialized solution and look at a very particular part of it, and it seems to work, but how spongy is this? Can I break it? Or is it, is it tough all the way down? Can I make a really strange black hole that still does thermodynamics? And I think when you start seeing that, it gives you confidence that this quantum description should definitely be statistical mechanical. Like, if black hole thermodynamics only happened for spherically symmetric black holes with no charge, then it becomes more like an interesting thing to put on a postcard. But if you can make something which is incredibly strange and add all sorts of strange matter fields to it, and then consider something which depends on time, and then still rederive the laws of thermodynamics from these systems, then you're really saying the underlying theory of this has legs. And I think that confidence that we get from this research is where it has a kind of real world benefit. It's not that we're going to see it, but it's guiding us towards answering a really interesting question, which is what's going on at the small scales. How is gravity actually communicating itself to the universe? And string theory isn't it yet. Like it hasn't answered all the questions. Maybe it will one day, or maybe something else will pop up. I don't think anyone, maybe except those who have tenure, anyone is willing to kind of throw down the gauntlet. String theory has had some amazing successes, and actually a lot of people now say that even if string theory has no physical dominance, the contributions it's made to mathematics alone mean that it's been really.
Yeah, it's interesting. I was at a summer school one year, and there was a lecture series on enumerative geometry, and he was mentioning that there was some certain some certain count that enumerative geometers were looking for, and then the string theorists made a prediction based on what they thought should be the case as corresponding to their physical models, and the algebraic geometers were like, there's no way it's that, it couldn't possibly be, what are you talking about, we don't believe you. And then sure enough, someone eventually came along and proved that actually, the prediction made by string theory is the mathematically correct one. So
I think, it's not for me to comment on, I don't think, but there's something incredible about how physical intuition has been able to guide mathematics. And it goes deeper than that. Like, why does physics have a mathematical description at all, right? Like, why can I explain the world around me with something as abstract as maths, and why is it so accurate? But I think when you're guided by the physical intuition and the insights that this gives you with certain areas of maths, that's an incredibly, so that's the backup plan I think that physicists have now. If string theory ends up not having a theory, I don't know, the history of string theory has been very strange. When it started in the 70s, it was trying to describe the strong interaction. It was never had anything to do with gravity. The reason that it's even called string theory is such a tangent here, it doesn't matter. You have the strong interaction between particles has this very strange fact that the force exerted between these two particles is independent of how far away they are from each other. So unlike the electromagnetic field, which has a quadratic drop-off, the tension, well, I don't want to say tension yet, the force remains. And so what someone said was, okay, if this is always there, if there's this kind of force exerted between these two things and it doesn't drop off, what if we just say that these particles are the endpoints of something one-dimensional? What if we say that this is a string with tension, like a rubber band, and the ends of this string can be thought of as the particles that we usually see, but actually the proper description is that this should be a string. And that was the starting point of one way to start thinking about these strong interactions, which are now dwarfed by a different area called quantum chromodynamics, which is incredibly successful and uses lattices to describe these particle interactions. And basically what happened was string theory was being studied with the hope that it could answer some of these questions, and someone accidentally in the motivations of the research, found that within the spectrum of the particles that string theory was producing was the graviton. It seemed to naturally have gravity living inside of it. And so when this was discovered, everyone changed direction, then suddenly was going towards the much bigger prize. And in following this, there's been some incredible movements within string theory research for the past 40 years. The big one, quite a long time ago now, like 25 years ago, was ADS-CFT, which is
Right.
this description or duality between gravity in d+1 dimensions and conformal field theories in d dimensions. And again, it's one of these things where, okay, even if string theory isn't the true description of the gravity that we have, the ADS-CFT conjecture has produced an incredible amount of research and insight into new areas of physics. And I think from the outside, maybe the question of whether string theory is right is a very interesting one. But when you're actually within the bubble, it is kind of like, it doesn't really matter. It's interesting, and that's enough. There's all sorts of very good criticisms of string theory, like the fact that it doesn't have particularly good abilities to give verifiable questions. But that's for someone else to deal with. I think it's a beautiful theory, and it's had some really interesting stuff. And yeah, so I don't have the physical motivation for my research is to give us a better foundations for our search for quantum gravity. It's not to have a better understanding of the black holes in the sky. But both are interesting, and luckily there's more than one of me, and people are looking at all the different aspects. So.
Excellent. All right. Well, one thing, if I can switch gears quite a bit here. So normally in these interviews, I like to ask people a bit about not just their work, but their journey to their work and to just math and physics in general. So I'm curious as to how you first got interested in mathematics / physics. You know, was it an early age? Were you a so-called late bloomer? How did that come about?
Yeah, so I kind of simultaneously can't ever really feeling like a mathematician, but also can't ever remember not thinking it was amazing. And I was talking to someone at work today. It's like sometimes I have to kind of like check myself and remember that not everyone thinks that maths is inherently interesting.
Right.
And then when I say that, I'm like, I probably was always a mathematician. I don't know whether you guys have it over there, but there was this book I read as a kid called The Number Devil. I can't remember who wrote it. I can Google it maybe. And it's about a little boy. I think he's having trouble sleeping, and at night the number devil comes to visit him and teaches him a maths lesson in his dream. And I can't really remember. Factorials might have been in the first one, and it's all done through the fact that it's an exclamation point, and it's very fun. But a couple of chapters in, they do Pascal's triangle, and I just couldn't get over it. And I remember drawing it everywhere and looking for patterns and triangular numbers and square numbers and drawing lines through it. And when I have memories like that, I'm like, it was pretty weird that I did that. Like,
yeah.
At the time it felt obvious, but yeah, so there's always been something magical about number theory to me. That being said, the motivation, or actually maybe not motivation, but the thing which helped me with mathematics was a kind of application to help with perspective. I think the kind of rigorous proofs that I'd come across, I felt like my memory wasn't good enough. I had a hard time remembering exactly what to do, or I'd do a proof and I'd miss something slightly, like I wouldn't be quite accurate enough, and the exam would come back and be like, yeah, I knew that, but I didn't realize that was important to say. There was always this kind of casualness to how I was approaching mathematics. But with physics, apart from having to remember to put units down, I found that kind of inherent love of the mathematics was there, but there was something a bit looser about everything that I did. I was able to kind of go, well, I know which way something would naturally fall, so I've already got an idea of what's going on, and then it's using the maths to kind of really piece that together. And I think for my whole I mean, actually, maybe I should go back before even getting close to doing. So we call them A levels here in the UK. I don't know what you call them over there, but before we go to university, we have this kind of 2-year chunk. Maybe you guys call it high school. I don't know.
Right.
but it's this kind of 2 years. So we call them A levels, and you specialize in subjects. So you now don't do everything; you just do a bit of stuff. So I did maths and the sciences. But before I did that, I left school and went to art school to do music. I was like, I'm going to become a rock star and play guitar. And weirdly, I was allowed to do one extra A level, and I chose chemistry because organic chemistry was like Lego to me, and I thought it was interesting. And I haven't touched it since. But what I did was halfway through art school, I just missed learning. I dropped out of art school and went and got my A levels and started doing maths. And there's been this tension in my studies where I think I've wanted to do pure maths, but I maybe haven't had the confidence, or I didn't feel like I belonged. And I ended up doing physics at university, and I finished my master's, and I was like, this was fun, but it wasn't mathematical enough. I want to do string theory. So I went and did a second master's in maths, theoretical physics at Cambridge, kind of scrubbing up to do high energy physics. And then I got just hooked on gravity. It was the geometry and the kind of, I don't know, I found myself naturally being really comfortable with everything that was happening and really sucked into the whole process. And I finished that master's and I was dying to get a PhD. I just thought it was the coolest thing ever and I wanted to keep studying it. And I didn't get one. I applied to like 20 different universities internationally. I had a girlfriend at the time who was living in France, and I was just like, I'm just going to apply everywhere and we'll figure it out. And I didn't get a single interview. And I was so disappointed. So I was like, well, I've had a strange path already, so I'll give it one more year. And after I got my master's, well, I now had two, I rewrote my research proposals. I contacted loads more schools. I think it was like closer to 50 this time. I did everything I could and sent it out everywhere. And I think I got 4 interviews of all the places I sent it to. and like, to put it in context, I really didn't do bad. I got a first in my first master's. I got a first in my second master's. I won a stupid prize from my university for getting the best score in my college. Like, I hadn't messed up. It's just super competitive. And there are some people who were just better than me, and I didn't make the cut. But I got a couple of interviews, and Thomas in Liverpool gave me an offer to study with him, and I was over the moon. He's a specialist in black holes and special geometry, and I was like super happy. And I spent 4 years working really hard and really enjoying my PhD. And amazingly, it was the same thing. I got to the end. I was applying for postdocs, and it was easily 70 postdoc positions I sent my research proposals to, and I didn't hear back from anyone. not a single interview. And I basically threw in the towel. I was like, I love this, but I'm obviously not. There's something missing, whether it's bad luck, or I'm into something that's not very trendy, or I'm just not good enough. I guess I'll never know. And that kind of led me to, I still love maths, and I'm studying it all the time. And during my PhD, I fell in love with cryptography. And now my focus is trying to make that as much of my life as possible. And actually,
so how did that come about? How did you, I mean, you're doing your PhD talking about black hole thermodynamics. How did you pick up cryptography? How did that enter your life?
So there was, actually how it started was so dumb. I think it was the first year of my PhD, or maybe the second, I can't really remember. There was a GCHQ, so they're like the NSA, but over here in the UK. They do puzzle competitions every now and again. And they released a book for charity, and inside the book was a set of puzzles. And me and a few people in the office started doing, someone bought the book. We had a coffee morning every Wednesday. We'd all sit there and we'd basically just chat about nothing. But one Wednesday, someone bought in the book and put the puzzle on the board, and we started doing it. And I had fun solving one of them, and then we ended up buying the book from the bookshop. And we basically all took a week off from our research and solved all the puzzles. got through to the last stage, and it was this crazy hard word box where you had to put all of the Greek letters from alpha to omega written in the smallest box possible, so you could reuse letters, like moving like a snake through the box. Anyway, we got something and it wasn't quite good enough and someone else won. But I was just hooked on these puzzles. And it had nothing to do with cryptography. And it had everything to do with being crazy stuck in my research and the emotional payoff from solving a puzzle. It was definitely that. Like, I had spent maybe 3 months grinding through some solution and finding it really hard. And then suddenly you get all of the serotonin rush from solving an easy puzzle. and I started looking for more puzzles online, and it didn't take long for me to eventually find capture the flag competitions. And I started looking into them, and it was a couple of years ago now. And it was stuff like web exploits, like SQL injection or cross-site scripting or whatever. And then suddenly there were these crypto ones. I was like, I know maths. Maybe I can do the crypto puzzles. And I didn't know anything about discrete maths. Like, I was sat there being like, why can't I divide? And then I was like, wait, how do you do division mod n? And then I was like on Wikipedia, and I was like, oh my God, there's this whole new world of maths, and I've never touched any of it. I've had this, like, by that point, 6-7 years of doing integrals and differentiation and solving equations and stuff. And then suddenly there's this whole extra thing, and I just got totally obsessed. Learning as much as I could. And it was just over a little bit of a year ago now, but I was talking to the other guy who I built CryptoHack with, Hyperreality, and we had solved some puzzles together, and we had fun, and we were both like, man, I wish I was better at cryptography. There's so much I don't understand. And he was like, yeah, me too. And there's like nowhere good online to learn it. There's CryptoPals and it's okay, but we both had issues with it, and we were like, well, why don't we just make one then? And we had this like crazy focused month and a half, February in 2020, where I was supposed to be starting to write up my thesis, but procrastinating and doing stuff like typography and choosing colors and stuff. I just sent off my second paper. So I think he was fairly quiet at work, and I was procrastinating on my thesis. And we built CryptoHack in like a month and a half. And the more I learned, the more I was just like, this is the coolest shit ever. And I was like, elliptic curves, I couldn't solve that puzzle. I wonder what they are. And I started reading about them. And then now I'd say I'm more interested in them than even in cryptography. Like, cryptography is cool, but like the elliptic curve stuff is just crazy cool. But it's been this kind of slightly obsessive evening project of mine for the past year. And simultaneously doing stuff that you will have learned years ago. I was like, what's a ring, and how's that to relate to a field, and like trying to learn what ideals are, and I'm like, okay, they kind of feel like primes, but they're not, and quotient rings, and then every now and again something feels like physics again. So like a quotient ring is a bit like a symmetric space where you take some group and take the coset, and I was like, okay, well, I've kind of seen these things before, but I use them in different ways, and yeah, it's been a kind of random walk through the whole thing. But the kind of core of it was, it started because I missed getting stuff right. Like, research is months of getting stuff wrong, and then suddenly you can do a CTF over a weekend, and they give you 500 points for solving a problem.
Right.
It sounds silly when you talk about it, but yeah, research is tough, and solving puzzles was easy, and I miss my research. Like, I've got this job, and it's good. The people I work with are nice, and I'm learning to code and stuff, but it's not like research. It's something special about research, and I miss it. So the cryptography stuff is my way to try and keep a toe in the water. Like buying textbooks and going through them slowly. And I don't know whether you've seen them, but there's those lectures by Richard Borcherd's. He's started putting up all those graduate lectures, and I've just been
I've been watching a number of them, and he did an interview with someone just the other day that I listened to. I mean, he did a Q&A as well, and yeah, a bunch of great videos. In fact, I'm a little bit peeved in some sense because, you know, I was starting to do some modular form videos and wanting to do some algebra, and now Richard Borchards is putting them up, and I'm like, well, what, you know, how can I compete with that? How am I gonna make, you know, some series with that's gonna, you know, outdo a Fields medalist? I don't, you know.
And I mean, obviously his lessons are great, but I don't think there can be too much educational stuff.
Mm.
Like, I can't remember the name of the guy. There's a guy who did you. It was a 3 episode thing on you could have invented homotopy theory.
Oh yes, yeah.
Yeah,
Actually, yeah. So I follow Bor Bark Tree.
that's it. Right.
Yeah, yeah. I
So
follow him on Twitter, and so actually, uh, I guess spoiler, upcoming spoiler for anyone who's watching. I'm planning on doing some group theory videos specifically because a number of months down the road, he's going to need some group theory for his series. So he
yeah,
asked me if I could do some videos about a couple particular topics to
yeah,
get people caught up if they don't know the relevant group theory. So yeah, amazing. I love his videos.
yeah.
Absolutely amazing. Yeah.
And actually, to bring it back to myself, just from the experience, I think part of what has made CryptoHack do well is that I wrote the lessons while I was learning it.
Mm.
If one of your listeners sends me an email and wants to learn about black hole thermodynamics, I'll be pretty shitty at first because I'll say, oh well, it's just this, and I'll be like, I've never heard that word before. What's that? And I'll be like, oh fuck, sorry, and start trying to fix that,
Right.
go off on some tangent. But with the cryptography, I was like, I can write these in the right order because I'm learning it at the same time. So
Right.
I'm going to do a Diffie-Hellman key exchange. What's a
Right.
key exchange? Why is it useful? And I have the background, like I understand why certain elements of it are useful. Like we have this finite group and we want it to be abelian, and I these work commutative if I'm a mathematician. Like, and these things aren't uncomfortable for me, but a lot of it was new.
Right.
And I think if you're thinking about making videos on modular forms, there will be things that you can explain to someone that Richard won't think about
Right.
because he of his experience. And I think from that perspective, there really can't be enough educational resources.
Mm.
Not everyone learns in the same way, not everyone explains in the same way. And
Right.
actually, even if you did a lecture series in modular forms and no one watched it, you'd understand it so much better. It would be
Right.
worth it for yourself.
Yeah.
So,
Yeah.
so
I mean, I'm
that
not you know, I'm not calling it quits entirely. It is, yeah, yeah. I mean,
but
at the very least, it really makes me understand the
yeah,
concepts.
yeah. So, but yeah, he's great. But so yeah, my path to cryptography has been a strange one.
Hmm.
But I think retrospectively, cryptography gives me that same handhold that physics gave me when I was trying to learn maths.
Hmm.
It, elliptic curve as a pure mathematics topic and studying abelian varieties is hard, and there's a
Hmm.
lot of stuff there which feels very uncomfortable for me.
Hmm.
But when I have that kind of focus point of, okay, I want to think about the elliptic curve discrete logarithm problem.
Hmm.
Okay, so this is the kind of core thing. I'm like, okay, it's just some hard thing that computers aren't very good at doing.
Hmm.
But then I'm thinking, okay, well, what's exactly happening? And when I have this kind of like pin in the map to move away from, I can
Right.
start kind of collecting small bits of information, and I can kind of become used to some of these things slowly. There
Right.
was a really cool CTF that happened at the beginning of the new year that did things like RSA and Diffie-Hellman, but rather than using integers, it used the Gaussian integers.
Hmm.
Like a small change, but I didn't know anything about Gaussian integers, so I learned a whole bunch of stuff and I wrote a big blog post about it. But if I had maybe come to the Gaussian integers on their own and thinking about things like the norm map and group homomorphisms and things like this,
Hmm.
I might have got lost. But
Right.
when I had this kind of thing of can I solve this small maths puzzle, and it introduced me to a whole bunch of new areas, that really helped me.
Right.
Um,
Yeah, I
and so
found there's nothing like learning when you have a particular goal in mind, when you're like, I need to do this thing, because I find it's interesting. It gives you an interesting mix of both learning how to get really the precise detail, but at the same time, you also learn how to ignore certain details, right? Like sometimes there's things that you realize, oh, okay, you know what? I don't need to spend 2 months on this. I can like, if I get like the idea of it, I can black box it. I can go forward. And
Yeah.
so it's interesting the way, at least I find for myself, when there's a particular thing you need to know how to do, how you can sort through the information and figure out, okay, this is the thing I'm gonna black box and just like,
Yeah.
use the tool, and then like here's this other thing, I better get those details, but you cut away from the fluff and you learn how to like, okay, this is what I really need to get from here.
Yeah, and I think with my research, that's exactly why my thesis ended up being so long. I kind of skated through areas of theoretical physics to get results for my papers, where I was like, I'm going to just trust that this is right, and I'm going to do it for my solution, and I'm going to write something. And then I came to writing about it. It was like, I black boxed that whole thing. It was like, I mean, it was fine for my research. Like we got the results we needed, but if they asked me to explain this, I can't sit the Viva and say, oh, sorry, I black boxed that. I don't know. And I think that the unpacking of those handholds is what made my thesis so big. But I think you're right. When you're the best researcher is the one who's able to look at the problem they want to solve and pick out the key components that need to be understood while skating over the top of everything else. And when I was first developing CryptoHack, there was a lot that I was skating over. There were things where I was like, okay, I understand this just enough. We can just keep going. And as I've spent more time reading it, and I've done stuff like I've got Silverman's text on elliptic curves now, and I'm working my way through that. And then to get through that, I was like, I don't really know what number fields are, so I got a book on that. And I've been reading these, and
yeah, so right here, yeah.
So I am sharing textbooks. I got this one recently, and it's this tiny little book, and it's got, there's this appendix written by other authors on hyperelliptic curves, but it's got a really amazing chapter on finite fields, polynomial rings, Grosvenor bases, and it all within the context of cryptography. And so many things clicked for me that just didn't in other texts. And you know, it's the same thing that Richard says, you have to read something 6 times before it clicks, right? So maybe I just got lucky, this was my 3rd time through or whatever. But it's been really cool to have the kind of cryptography spine that I've kind of been branching off from and covering some things. And part of me thinks that potentially in 5 years, you know, CryptoHack will be bubbling away and helping people learn, but I'll be off on some new tangent studying maybe something purer than I ever thought I'd be able to get to. But the path is dictated by, like, I really want to understand isogeny stuff better. I think the crypto systems being developed around that is magic. So yeah, there's all sorts of stuff. But personally, for me, the way that I learn is if I can start trying to unpack a problem, and physics and cryptography have both been vessels for me to do that. So I think it feels strange talking about it step by step, but actually understanding myself as someone who likes learning maths but needs something tangible to kind of tie it to. I think cryptography does this in exactly the same way that black holes did. Like we were talking about, nothing about my black hole was physical. It was just physical enough that I could start doing some gnarly things. Well, something you said earlier, maybe remember that for total mathematicians who are interested in some of the thermodynamics that I proved, one of them is that you can prove the existence of a contact geometry in your space of solutions, which for people who don't know is kind of like the odd dimensional version of a symplectic geometry. And so the first law of thermodynamics, this relationship, it's basically the conservation of energy for a physicist. When you write it in terms of differential forms, you then actually prove that there's this existence of a contact geometry where the coordinates in the space are the conserved charges of your thermodynamic system. So I don't know, just as a brief aside on how geometric these laws really look from the point of view of black holes. Like these, yeah, it's remarkable. But yeah, if anyone has made it this far and they're still listening to me, go check out CryptoHack and play some cryptography. It will inspire you to become a better mathematician, if nothing else.
I haven't had the chance to really dive deeply into CryptoHack yet, but it's on my summer to-do list when my thesis is written up, and because as I mentioned, before we started chatting, cryptography is a backup plan for me, basically. If the PhD doesn't work out, or if I finish it and I can't find a job, it's like, I think it makes the most sense to try and transfer into that field. And so I'm planning on spending some time on CryptoHack as help prepare me for alternative futures.
Yeah, and academia is pretty brutal. Like, okay, I have my story, and it hasn't gone exactly how I thought it would. But I have friends who I studied with in Liverpool who are incredible, who worked crazy hard every day and wrote loads of really good papers, and who have now spent 6 months applying for positions and haven't heard back from anyone. And even the people who do get positions, it's like a 12-month, 18-month position sometimes, with no hope of a second position. And it might be 1,000 miles away from you and your family. You pick up and you move, and you're immediately applying for a new position. And trying to publish a paper and doing teaching responsibilities and writing grant proposals. And okay, maybe you get a second one. But I have friends who on their 4th or 5th postdoc didn't get another position. And that was just it, the end of the road. And they're like hitting their 40s. And the universities earn so much money, and it feels like so little of it goes to supporting academia. It's not, for certain people, like the best of the best of the best, academia is still an incredible opportunity to put these people in a position of giving it their all for research. But I have some talented friends who have been forced out rather than chosen to leave, and that seems like a shame. And then you start factoring other stuff in, like you want to have kids and a family. Like if you're still doing postdocs and dancing around, it's but that being said, if things go just right and you do your research and you give a talk and someone loves your talk and they give you a position somewhere, that becomes a postdoc, and 2 years later you're on a professorship. Like your life can then resolve around maths forever, and I don't think there's anything cooler than that. So everyone I talk to, if they're umming and ahhing about a PhD, I really don't think you can do anything better than giving yourself 4 years to think about something that you find is really interesting. As long as you're doing the PhD because you love the subject, and you're not doing it because you want to tell someone you're a doctor or whatever. like if that's your motivation, I really don't think there's anything better than you can do. Even though I didn't get the position and now I'm doing something different. Like looking back on those 4 years of total freedom, reading whatever I wanted. Like I'd have moments where I'd be sat there in the office reading a paper, and I'd be like, "Holy shit! I'm getting paid to read a paper about black holes. This is insane!" Like, okay, it wasn't much money. The PhD salary in the UK is low, but like, I was able to buy my food, pay my rent, like just by thinking about maths. Like that's so cool. So I'm really happy that you have a position, and you'll have a good time, regardless of whether you become a cryptographer by accident. Or not being a professor in number theory, right? So, I don't know. There's criticisms of every business, every company, right? Like working at Google isn't perfect, and working at some university isn't perfect. So, we'll see.
Well, yeah. I mean, there's really only space for so many people to be mathematicians,
Yeah, I guess so. I'm not sure I agree. I feel like anyone who wants to be a mathematician should be given space to do
Right, right. Well,
it.
yeah,
You're right. I just wish it wasn't the case.
yeah.
And also, like, I remember when I went to my undergraduate, we had this, like, it was like this first lecture. I don't know how normal this is. And the guy basically stood there and was like, all of you were top of your classes, and you're now here. You
Mm,
can't all be top of your classes.
mm,
Don't worry about it. Just be here and enjoy it. It's
mm,
not about being the best. You're not bad because you're not the best. And I actually did pretty well in my undergrad, and I was still kind of close to the top. And I went and did a PhD, and I finished my PhD, and I wasn't close to the top. I
mm.
had a couple of good papers, and I had friends who had several amazing papers. It's like, okay, um, you can't always float to the top, and if the world is such that there's only space for those few people, then that's still what's best for academia
Mm.
in the long run. Um, all I want to find is a way for me to think about maths, and I think cryptography, even in an applied sense,
Mm.
is an avenue to think about maths most of the time.
Yeah.
Um, and that's really why I did crypto hack, because it was a way for me to think about maths most of the time.
Mm.
Um, and if it can become my day job, whether it's cryptography with crypto hack or because a company wants to pay me to be a cryptographer, then cool. Um, yeah, so it's a balance, but yeah, it's a strange thing. I don't know. I was talking to my fiance about this, like, since not doing maths all the time because I've graduated.
Mm.
When I shut my computer down at the end of the day, I pick up a textbook and I read maths. And part of it feels like a choice, but it doesn't always. Sometimes it just feels like I don't have a choice but to go and do a bit of maths, like
Mm.
an itch that needs to be scratched. And if I spent
Yeah.
all day writing a program, then I haven't done enough maths, so I have to top it up.
Yeah.
And it's weird to have that in my life again after obviously being satisfied by my research. Um, and I guess you watched that same interview with Richard that I did. It's like 2 hours long. I think I got about halfway through, but
Mm.
I listened to him talk about it and the way he lives his life and has maths kind of focal point. I don't think I'm quite that dedicated.
Mm.
Otherwise, maybe I'd still be doing this. But there's definitely a kind of, I don't know. I don't fully understand my relationship with it yet. It doesn't feel like my relationship with music, where I put on music because I want it to be on, but feel like I could turn it off.
Mm.
Like, there's this feeling that if I haven't thought about maths that day, something feels off.
Yeah.
And like I'm opening Wikipedia to read a page while I'm on my phone because I
Yeah.
realise I haven't learned something. And and I don't know. I don't know whether that's healthy or whether, age will mellow me out.
Mm.
But it is interesting, given the reflection of a change in circumstance, to see that what made me read papers all day hasn't gone. I'm just not
Right.
being paid to do it anymore.
Right.
So, yeah, like if you won the lottery, what would you do? And when I had a PhD, my answer was probably the same thing.
Yeah.
And now my answer is stop doing work so I can read more maths.
Yeah.
So
Yeah,
yeah,
that's exactly, because as everyone does, you fantasize about what happens if someone dropped a big pile of money on you
yeah,
out of nowhere, lottery, or some turns out you had some uncle no one knew about that died, left you a fortune,
yeah,
whatever. Yeah, I would still be, I've got all these textbooks on my shelf, and half of them have nothing to do with my research. I would read these textbooks, like that's
yeah,
I
right,
would spend time doing that.
yeah, yeah. Yeah, I feel like it's a completely natural feeling when like I talk with someone like you, but I'm not sure how I fit in globally. I
Mm,
don't. Yeah. So it would be interesting. I feel like it's interesting to think like post PhD, but still loving research,
mm,
where I'll end up. Not sure. But for now, cryptography seems to be filling that hole
mm.
for now. And maybe if I understood it as well as I understood my research, it would be something else, right? Like there's, you know, I don't feel like I need to keep reading textbooks on the same area, and I don't have time to do research in the same way. Like solving a research problem, you can't do in an hour in your evening. It's not. Sometimes you do 8 hours and make no progress, right? You can't do that kind of stuff. So.
There was an interesting, I think it was, you know, Edward Frankel?
No.
Heard that name? So he's a mathematician who, I guess he works in the Langlands program, but is also very interested in physics and has made some more contributions to mathematical physics. And he has this book, Love and Math, that I've been going through recently. And I can't remember the mathematician he's talking about, but in that book, he mentions this one mathematician who apparently had lots of beautiful proofs and lots of beautiful counterexamples. And his routine was in the mornings, he would work on trying to prove a theorem. And then the afternoons, he would work on trying to disprove it. And that was his, like, every day, that was his strategy. And it paid off, apparently.
That's interesting.
Yeah.
I know that's what Yao did when he was studying the Calabi-Yau conjecture. But he basically was like, that seems absurd. There's no way that you can have a non-trivial Ricci flat manifold. No way. And spent years trying to prove it. And when he couldn't, he was like, oh, maybe I'm wrong. And turned direction. And then that's when he started trying to prove it. But it was only after he really felt like he exhausted the fact that he thought that it wasn't possible.
Right, right.
Yeah,
there's a similar story, again, someone else whose name I can't remember, but I think it was something to do with geometry of the seven sphere, if I recall correctly, or well, maybe the seven's coming from somewhere else. It was a geometry problem, in any case. I think it had to do with spheres, but yeah, this person was trying to disprove the conjecture for I think 7 years. That's where the 7 is in this story. And yeah, so they tried disproving this for about 7 years, and then one day they're like, well, maybe it is true. And that day they sat down to prove it, and about 2 hours later they had solved the problem.
Yeah, amazing. I mean, you do research and you're stuck on a problem, and you can spend months on it. And your light bulb moment might only take like an hour, and you sit there and you finish it. And you're like, how did I not like? For me, one of the things I spent a load of time chasing was just minus signs in strange places and trying to make sure them all. And sometimes
but my research involves something called super geometry. So basically, it just means things are Z2 graded. There's just an even and an odd component. And what that really just means is there's a whole bunch of minus signs you have to worry about now. And there was one time me and my supervisor sat in a coffee shop an entire morning, like easily half a day, chasing around a minus sign. And that wasn't even the end of it. I went on to have to go chase that minus sign around the way, and like, was the difficult thing these abstract manifolds, different dimensions, and no, that wasn't the hard part. The hard part was this stupid little minus sign that we spent ages trying to pin down.
Yeah, it happens. It's funny. Is your super geometry, so is that related to like orbifolds, or is that different?
I don't really know. I don't. So none of what I did had anything to do with orbifolds. It was just basic manifolds, and your vector bundle just has the vector spaces have an even and an odd component, and then the geometry you're doing has to respect it. So there's a notion of a connection on those vector bundles. But the way it acts on the vectors has to respect the even and odd components in some particular way. Yeah.
That's interesting.
Yeah. So I think
So specifically, I was just looking at vector bundles that are Z2 graded, but I think more properly supergeometry typically refers to, I think, specifically having a Z2 grading on the tangent bundle, and some stuff comes out of that. So yeah, I don't know if the more general story helps you do things about orbifolds. I'm not sure.
Yeah, I mean, so from the physics point of view, orbifolds and orientifolds pop up when you want to break supersymmetry, which is to do with the spinors in the theory. By using the Z2 grading, you remove certain parts of your spinors, and that reduces the number of supercharges you have, which breaks how much supersymmetry you have. So it might be related, but I don't know, just interesting. Yeah, it's cool. More to learn. Yeah, I mean, do you have any more questions? I feel like we've done loads of backwards and forwards chatting. I'm not sure how much I've communicated.
Yeah. Well, there's a so I suppose one thing I sometimes like to ask people is what they would be doing otherwise if they couldn't do math, physics, or let's even lump cryptography in there.
Sure.
So I suppose it would be music for yourself if you couldn't pursue mathematics.
Yeah, that's a good question. So yeah, I did music for a long time. I was in a heavy metal band when I was a teenager, and I did more ambient stuff as I got older. And I do poetry and stuff. So I have a book of poems that I put out last year, and I run a website called Neutral Spaces, which is well, the original idea was it was a portfolio platform for writers, because a bunch of my writer friends were like using WordPress and it was ugly and horrible. I was like, hey, I know just enough web stuff that I can help you out. And then it grew and there's like 500 people on it now. It's good fun. And there's writing projects and a blog and stuff. So I might be doing stuff to do with writing. But I guess the reality is, outside of the kind of maths world of cryptography and stuff, there is something quite calming about just general programming. I don't know whether I don't love it like I love maths. Writing a good program doesn't feel the same, but like the work I'm doing as a software engineer, it's satisfying. And when I get stuck on writing a good, clean program, it ticks some boxes. But yeah, if I wasn't allowed to do anything technical, it would be probably, I don't know, I always joke that making money out of art is the most miserable thing you can do. So I probably wouldn't actually do it. I don't know, maybe I'd open a cafe. That would be nice.
Oh,
so
yeah.
people need coffee. Maybe have a cafe with a library in it, and people can read books. And I probably, I don't know, when I was a pretentious student, I used to talk about wanting to have a cafe where people could come and give lectures and things that they found interesting. And so I don't drink booze, but I always wanted somewhere to go and sit in the evening. So a cafe that was open late and had lectures, some kind of intellectual space. Although it sounds like I'm cheating again now. I'm getting a bit close to maths. So, yeah, it's hard. What would I do if it wasn't for maths? I guess I don't actually know. I can't imagine it not being there somewhere.
And one other thing I like to finish with as well, I typically ask people where they fall on the is math created or discovered divide. But it sounds from earlier in the conversation you're more on the discovered end of the spectrum, if I had to guess.
Yeah. It's such a hard question, isn't it? Because I don't know, I guess, so cheating for a moment, communicating as humans, language is definitely created because different nations speak different languages. English isn't natural, but English happened naturally. And maths has happened naturally. And slightly weirder than that, it happened naturally in a language agnostic way. So the ancient Greeks were doing things in geometry that people causally separated from them were doing too. The Greeks didn't tell someone about geometry, 2 other people did it. Similar. And things like Ramanujan and the work that he was doing was in some sense independent. Quite how independent his research was, I don't think we properly understand. And I know the nice story that he knew nothing and derived it all himself is what's told, but he also did have access to a library and teachers, and so he obviously had an amazing progress on his own. But so there definitely seems to be something discovered about it, but I'm not sure. I'm not, like, I was thinking about this today. Someone shared a thread. It was about aliens and cryptography, and they said that alien symmetric cryptography would be different. The way that we scramble data with a key would probably be completely different. But the asymmetric stuff, RSA, elliptic curves, etc., will probably be pretty similar. These trapdoor functions. I'm not sure I agree, but when I think about whether maths is discovered or created, this kind of notion, counting feels discovered. This notion of quantifying things and collecting them together and stuff. But the notion of like a hard problem, that I'm not so sure on. So like, can I imagine an alien species who very early on had a very efficient method for factoring integers? Yeah, maybe. Like, or like the Riemann hypothesis. Maybe the Martians who discovered that proved it on the same afternoon that they put the problem about, or maybe disproved it. Doesn't matter. So like, there being like how we experience maths. I don't think I feel confident that it's universal. I don't think a hard problem for us is necessarily a hard problem for somebody else. Like a really simple thing, when we're doing geometry, lines, surfaces, like objects, super easy. 4 dimensions, completely gone. Like it's discrete, right? We go from like, yes, I can imagine it, to absolutely no idea. Like anyone who works with 4-dimensional objects, they can go, okay, I'm familiar with what I'm supposed to say, but I don't know what this looks like. That doesn't feel locked in. Like maybe there's someone who can, like maybe bugs see in 15 dimensions and we can't communicate about it. So I guess what I'm trying to say is the properties are self-consistent, and in that sense are discovered through the process of setting your boundaries. If you allow the natural numbers to be what they are, there's no other way for natural numbers to exist. So I don't think they were created. I think they are naturally self-consistent with a set of ideas, and the simpler the idea, the less likely it will be for someone to have a differing point of view. Counting, I think, is the easiest one to hold on to. Platonic solids, like there really is no other way that you can do them. Our experience with these problems, though, that I'm less like, things which feel obvious to us or things which feel difficult to us are so related to our experience of the world and how we can think about them. I don't know. So like, I feel if you go deep enough, I feel like I'm a Platonist. Like I feel like these things are just there, and we happen upon them. And when I think about the way that physics interacts with maths, that just feels even stranger. But how we experience maths, that feels very human. That doesn't feel derived. The difficulties, I guess that's what I'm saying. The difficulties we have with research, that's got nothing to do with maths. That's all on us. Whether it's the Langlands program or thermodynamics of black holes, like we made that problem, and we're the ones finding it hard. Like the Riemann hypothesis is already there, whether it's undecidable or true or false. I guess I really feel like that's happened. We just don't know about it yet. I don't know. I don't know whether you've seen, but a really popular thing I've seen on Twitter is the ultra finitism.
Oh yeah.
I don't want to get it wrong, but from my understanding is people say if it can't be computed, then it's not real or it doesn't exist. I don't want to say real because obviously we have complex, but like that feels very wrong to me. So if I'm putting myself in a kind of philosophical spectrum, this idea that something has to be computed to be maths feels very wrong. I don't know where that puts me on the derived or discovered. I mean, maybe that's like the hard line, right? Like the ultra finitism is even more than discovered. It's tangible. So it's like tangible, discovered is always there, right? Like I don't think you can be an ultra finite Platonist. You can't believe that these things exist, but they only exist up until what we can put into a computer.
Right. Yeah, I would say the ultra finitists are probably pretty opposed to Platonism.
Right.
Yeah.
Right. So
I'm actually, I must say, I'm quite sympathetic to the ultra finitist cause, and the problem is, I guess, I like doing infinite math too much, and so I'm gonna keep assuming my axiom of infinity and probably my axiom of choice and axiom of power sets, and I'm gonna go and do a whole bunch of interesting math with that. But there is a part of me that sort of thinks, well, yeah, our physical world seems to be finite in many ways, and sure, we can make things continuous and get good approximations to to do our physics and like general relativity or some functional analysis for quantum. But there is a part of me that thinks at the end of the day, the capital T truth is perhaps something that's more just computational and finite in extent.
Yeah, and I guess really the question is then it comes back to, is maths something that we experience or is it a tool? So in a certain sense, I almost feel like our ability to imagine infinity is enough to say that mathematically infinity is well defined. As long as we can work with it in a self-consistent way. As long as it doesn't cause corruption within the work that we do, then I have no problem with it being within our mathematical toolbox. And then the question, can we find it? Can you find a seventh sphere? I mean, I can write the coordinate system for a seventh sphere, right?
Yeah.
And I can put it in Mathematica, and I don't know, I can bend it a bit. I can look at the manifold, and I can study the causal geodesics on it if I want. But I mean, if you're comfortable saying that exists, but that, I don't know, well, there's like tree 3 in Graham's number. You're like, those don't exist because they're too big. I'm a bit like, well, I mean, just because you can't look at the number, you can't look at the seventh sphere, right? I don't know. I think you're picking and choosing a bit. You're getting uncomfortable with something really big, but that's totally physical. Like I can imagine these big numbers by literally just counting up, right? As long as you don't stop counting, the number eventually gets there. But if I instead think about something, I don't know, like a Calabi-Yau manifold that I compactify over in my string theory, and I can work with it, and I can put it in my maths, and it produces my number of supercharges, and I end up with something that looks like the standard model. But those 6 dimensions which have been wrapped up, like, it doesn't make any sense. Not in any kind of computational way, not in any finite way, I believe. Like I don't think you can have a kind of notion of these objects. We just have an idea of how they behave. And I think if you allow that, then you have to also allow big numbers. Okay, we can't imagine it. Graham's number is too big to imagine, but we understand what it is.
Right.
We achieved it with a set of finite instructions. We just don't have the space to hold it.
Right.
I don't know. So that's the thing that I think I feel uncomfortable about. Like if you can describe how to construct something, I don't know. Like I have a smaller computer than they have in MIT's basement, but MIT doesn't have bigger numbers than me. Like I don't know. we don't have like a kind of local finitism based on the RAM and hard drive that I have access to. Like I don't know, go buy an SD card and I get slightly bigger numbers. I don't know. I'm being facetious. I understand all of the sides, but I guess something fundamentally feels wrong about terminating something because we don't understand it. I don't, and yeah, maybe that comes back to your original thing. I don't feel like the limit of a human's understanding is the limit of maths. We know stuff now that Fermat didn't know about. Doesn't mean that those things didn't exist when Fermat was around. Like, okay, the techniques Wiles used to prove his last theorem were unknown to Fermat at the time, but his theorem wasn't nonsense until Wiles came around and proved it. We didn't know how to do that yet. I mean, if you don't know how to prove something, you don't know how you compare that to ultra-finitism, right? Like this idea of, okay, I can't construct it, but you can't even prove something. Where does that live in this space of undecidability? I don't know. It's where you draw your line in the sand, I guess. But what about you? I don't know if people ask you back, and if they do all the time, then short answer is fine.
Yeah, I mean, I guess I've talked about my own views in just about every interview. So yeah, just as I guess a quick synopsis is typically I'm most inclined to think that math is just a language, and there is a part of me that in some sense thinks it's unsurprising, the so-called unreasonable effectiveness of mathematics, because I think, well, yeah, we built math to describe the world, so it shouldn't be surprising that when later on the math continues to describe the world. Sure. But then of course
yeah, I agree with you.
It is kind of freaky though at the same time that it does, you know, how we can predict gravitational waves 100 years in the future. So I would say most of the time I think it's just a language, it's just a tool, a description that we came up with, but it's not that I don't question my own beliefs.
Sure, yeah.
On that topic frequently.
Sure. And maybe if you'd asked me the same question on a different day, I would have had a different answer. Like if I sounded like I spoke with confidence, I don't feel like I actually know. Maybe it's one of those. I prefer it to be discovered. If it's just man-made, then it could have an end, right? Like, I don't know.
Well, I think that might be a good place for us to stop for today. We've been going on for a while here. So thank you very much for joining me and having this discussion, talking about your research and just being someone interested in math.
Yeah, I appreciate you taking the time. I know that I have a tendency to chat on, so I appreciate it.
Well, hey, I mean, this is the place to do it.
Yeah, sure. No, I appreciate it, dude. And good luck with the PhD. I'm really
thanks again.
Right, speak soon, dude.